Hello. Oh, that's weird. Okay, so thank you everyone for coming to Running Containers in AWS. There's nothing superhero themed about this presentation, which is why I have to compensate by wearing a cape. Now, interestingly enough, this is a presentation about containers in AWS, but this is a Google cape. So, my name's Andrew May. I'm AWS certified. I'm the Cloud Solutions Lead and Senior Solutions Architect at Leading Edge. I'm also an AWS Academy instructor at Columbus State Community College. So this is kind of our agenda for the presentation. All things here are based around Docker, but this isn't really a presentation about Docker. A lot of this is going to be talking about orchestration services within AWS, these different options they give you for running containers. In particular, how you manage persistent services. A couple of things about discovery. If you were in the previous session, there was a talk about that covered Cloud Map. We're just going to skim over that a little, and also App Mesh. And then a couple of transient usages of containers in AWS. This is not an intro to Docker. I'm going to assume that most of you have some experience with Docker, have an understanding of what it is, perhaps know how to build Docker files, container images, and at least run them locally. Now, I may not be able to see very well because I've got a light shining in my face, but quick show of hands, who's actually running containers in some form in production? So that's a good number. And how many of you are using AWS? Again, a good number. Okay, thanks. So just kind of a brief recap about a couple of different types of sort of containers and the way they run. So in this first example, we're running a transient Docker container. And what I mean by that is it's a container that runs, does a little bit of work, can be just for a second or so, and then ends. After that, it's completely gone. In this case, I'm using the whale-say, which is based on cow-say. And as you can see, this was originally for an AWS meetup, which is why it says hello AWS meetup. And it's pulling down the layers of the Docker image from Docker Hub because I didn't specify a particular source. And then it's going to extract those, and then it's going to run the container. And the reason it's pulling these down is because I didn't have this image locally when I first ran this. So it ran once, it just ran for a second or so, run it again. This time the image is cached locally, so it doesn't have to pull it down again. So where images are stored is an important thing we need to bear in mind. Now, the other sort of thing we're going to talk about here is services. So this one's the example of running a service. In this case, we're just going to run Nginx. We're going to map port 8080 to port 80. And then we can see in another tab that that's now running, and we've got that mapping. And we're going to do a curl to localhost and just pull back the index page of Nginx that's not been specially configured at all. And when we go back to the original tab, we can see that it's logging the requests here. Now, the important difference here, sorry, my cape's getting in the way, is that this is going to keep running until someone stops it. Now, it might die, and depending on the flags you give to the Docker command, it could restart, but it's something I had to manually start. So this isn't really a good fit for running in production. Now, I mentioned we have to worry about where our container images are stored. Here we've got the blurb for the Elastic Container Registry. So this is a fully managed Docker container registry on AWS. So ECR's registry hosted in every region in AWS. This is important because as you saw when we ran that cow-say or the whale-say, it took a while to pull down that image. But if your registry is local to you in AWS, then it's going to be much quicker to pull down that image. So for example, if you're running in multiple regions in AWS, you probably want to push your images to each region where you're going to run them so that they're easy to get to and quick. Images are secured using IAM policies, so that's the standard for pretty much everything in AWS. And so the service that's going to run those containers and any users who might be pushing or pulling containers are going to need to be granted access using IAM. Now, the registry is the service as a whole, and it contains multiple repositories, kind of one per image. And then that repository can store many versions of that particular image. Now, if you're storing many versions, you're going to accumulate those images over time. and they take up space, and that's one of the main things you actually pay for here is the space consumed by your Docker images. So you want to use lifecycle policies to clean those up. And so you can use lifecycle policies to clean up untagged images or based upon the length of time they've been in the repository. Now, if you want to actually use this to push up a new image, you first have to log in. And one of the ways you would do that is using the AWS CLI. And this gives you back a Docker login command with a temporary token that lasts for 24 hours. And you then can push using the standard mechanism with Docker push, where you prefix with the repository URL, which in this case will contain your account ID and the AWS region. Here's a quick screenshot of an example of a repository storing multiple versions of an image. In this case, the primary version number here is just a build number, and we're also re-tagging latest, so that's kind of a floating tag. Okay, so I mentioned once we go to production, it's no longer really good enough to just be logging onto a server and doing that Docker run command. Even if it can automatically restart, you want something more sophisticated than that for supporting things. And orchestration is what you would call this. And orchestration provides you a number of different things. So it provides you the ability to configure your services, the ability to schedule when they run and how many run, to do a new deployment. Perhaps you have a new version of the service or a new configuration for the service. You may want to scale up and down based on demand. Storage volume mapping, if you've got persistent storage, and secret management, think perhaps database credentials for the database your service is going to call. High availability, obviously one of the key regions you might go to the cloud is for high availability. And then if you're going to run multiple copies of something, you're going to want to integrate into a load balancer. In terms of options AWS gives you, I've kind of divided them into this kind of two main categories. ECS, which is the Elastic Container Service, and Kubernetes. Now, ECS is a custom AWS service for running containers. There's the ECS service itself, AWS Fargate, which is a serverless option for ECS that you might have seen in the previous Cloud Map presentation, and then also one of the Elastic Beanstalk options that's available uses ECS behind the scenes. There is another Elastic Beanstalk option which we'll also briefly touch upon that doesn't use either of these. And then in Kubernetes, you've got the Elastic Kubernetes service. It's actually got a much longer name than that. And I've got a grayed out box for Fargate there because there was a promise of Fargate being available for EKS. I don't believe that's come about yet. So you don't have a serverless option in Kubernetes yet. So I'm going to talk about ECS first. So the Elastic Container Service, highly scalable, high performance, but it's a custom AWS option. This is kind of the original service for running containers in AWS. And before it was made into a public service that you could buy and use, it was actually the back end for running AWS Lambda functions. So they announced Lambda functions at reInvent one year, and then the next spring, I think it was, they announced the ECS service was publicly available for you to run your containers. So every time you're running a Lambda function, you're actually running a container behind the scenes. The ECS service itself is free, but you pay for the resources you use alongside it. That's true of a lot of orchestration options within AWS. So in this case, you might be paying for a series of EC2 instances or the Fargate runtime environment that you're using. There's strong integration with other AWS services. That's really one of the big benefits of using ECS. And this might be IAM permissions. For example, you've got two services. One of them's talking to Dynamo, another one's talking to S3. You want to grant the one service permission to access that Dynamo table, but not to be able to access that S3 bucket, and vice versa for the other one. They may be running on the same EC2 instance, and if you were just to apply permissions at an instance role level, those permissions would bleed down to both containers, and they'd both have access to each other's services. But by being able to specify permissions at a task or container level, you can limit the access that they have, and that's a more secure way to configure things. The other big thing that's really important here is once you're running multiple copies of a container, you want a load balancer in front of it, and you've got options and support for both classic ELBs, application load balancers, and network load balancers. You've also got some auto-scaling options that works very similar to EC2 auto-scaling. Somewhat basic, but it You can use custom metrics in addition to things like CPU utilization to scale up and down based on demand. Now, this kind of ugly screenshot is the ECS cluster in a console. This is just a development cluster running 3 different services. There's a lot of terminology here. Some of it's kind of confusing, and I think it's evolved over time. Now, I've mentioned Fargate. Well, originally, Fargate wasn't part of ECS, so they kind of bolted it in, which is why it's a bit weird here how it shows both Fargate and EC2 options in the same UI. And when they talk about container instances, they also may call this ECS instances in other places. These are really just EC2 instances that have been registered with your cluster as being available to run containers on. There's also the concept of tasks, and these are really that you're running containers of which a service may have multiple tasks running, and then tasks are defined by task definitions. So let's dig into this terminology a bit more. So a task definition is really a template for how you're going to run a task, which in turn may be incorporated into a service. The definition is going to reference a container image that lives somewhere. Now, typically, we're going to use ECR for that, so the task definition is going to point to an image in ECR. And then when you actually start up a task, if you're running on EC2, there's an agent that runs, sees what the definition says, oh, I'm going to pull down version 3 of this container, and then it pulls it down and starts it. The definition is also where you're going to supply various configuration like port mappings, CPU memory requirements, IAM roles, and volumes. And then task definitions are versioned, and this is important because when you want to deploy a new version of your service, you're typically going to create a new version of the task definition and then update the service to say, now run this version, and it will automatically deploy. Now, a little more about ECS services. So these are these long-running containers. Often it's going to be a web service of some kind, typically fronted by a load balancer. So think of these as a long-running collection of tasks. Now, a task itself could be more than one container. It might have sidecars, other containers that run alongside it to provide some kind of service. This might be an X-ray daemon or a logging agent or something like that. But in this example, we've got 3 different tasks running on the same EC2 instance. They all say port 80. Well, we've immediately got a problem. They can't all use port 80 because there's a port collision. In fact, none of them can use port 80 because they're not running as root, so they can't use a low-numbered port. So what do we need to do? We need to map it to a port on the EC2 instance so that the load balancer can talk to it. This is assuming we're using the typical bridge networking mode, where it uses the IP address of the host. Now, one of the nice things they introduced later on with ECS when they added application load balancer support was the ability to just say, on the host, I don't care about what port I'm using. Just specify 0 and it will pick a high-numbered ephemeral port. And in this case, you can see it's given those 3 high-numbered ports. And then it's automatically keeping the target group in the application load balancer up to date with that port number as new containers start and stop. Before you had that integration with application load balancers, if you were using classic load balancers, you'd have to specify that port mapping explicitly. So service A, you'd say, well, perhaps it's port 8080, service B, port 8081, etc. The problem there was if you were going to spin up a new copy of service A, it couldn't run on that same EC2 instance, even just for a short period of time, because they'd clash on the port number. So it meant when you wanted to do a rolling deployment, you had to have spare EC2 instances to do that update. Some of the other benefits of ECS over other services is all this infrastructure, all of these tasks, definitions, and tasks and services, and how they hook up to load balancers are all created using CloudFormation, or can be created using CloudFormation. So it's the same infrastructure as code tool that you might be using to declare your load balancer, declare an S3 bucket or a DynamoDB table. And when you specify a service to use a new task definition, it's going to perform a blue-green deployment for you automatically. And that's going to ensure that your service remains up and running. Now, this isn't very sophisticated. Essentially, what it's going to do is it's going to spin up copies of that new task. Perhaps it's a different container version, perhaps it's a different configuration, and it's going to run a health check. And if that health check passes, it's going to then drain connections from the old version of the task definition and switch over to the new one. But it does mean that if those health checks failed, it's never going to stand up the old, never going to tear down your original version, and your service is going to remain available. You can place your tasks in different ways. So you've got a couple of different options here. You might spread them across availability zones, and that gives you better high availability should entire availability zone go down. Or you might want to bin pack things and crush them together on as few EC2 instances as possible. You can also have non-homogeneous clusters. Now, it's common that you'd register an auto-scaling group that traditionally has just contained one instance type with an ECS cluster, but you can actually register multiple auto-scaling groups with the same ECS cluster. And for example, you might have some that have GPU attached so that you can do GPU tasks, but you want to make sure that the containers that require that go to the EC2 instances that have GPUs attached. One other feature that really just applies for EC2 and not Fargate is the ability to run daemon services. So you saw in the previous slide I had a task with 2 containers, one of those being something like the X-ray daemon. Well, if you want to do that for every service and you have multiple services running on the same EC2 instance, that's kind of wasteful because you're running lots of copies of the same container. But if you use a daemon service, it just runs a single container on each EC2 instance in the cluster, and so you just need to run one of them. Now, metrics here, there's some built-in metrics that go to CloudWatch metrics, and then logs can also go to CloudWatch logs. So again, it's all strong integration with AWS. Now, I've mentioned Fargate a bunch of times. This is the official description for it. It's really a compute option for ECS where you don't have to manage the underlying servers. So, of course, there's EC2 or something similar under the hood there, but you don't have to worry about it. So this is kind of serverless. And when you configure it, you specify how much CPU and memory you get. Now, with EC2, you can really pick any quantity of CPU and memory. It's kind of just a number. With Fargate, you have to pick particular values, so half a virtual CPU and a gig of memory. You only get so many different choices, and for a given CPU choice, you get a subset of the memory choices. With EC2, you can be much more fine-grained with how you allocate things, and you can also do over-provisioning, particularly with CPU. So imagine you've got 5 services running on the same EC2 instance. Not all of them are necessarily busy all the time. So when one's busy, it can be using pretty much all the CPU on that EC2 instance. And when another service is busy, then that could be using all the CPU. Now, that does mean they could interfere with each other and they don't get guaranteed CPU. But compare that to Fargate, where everything's isolated. If you say it's getting half a virtual CPU versus running on an EC2 instance that has 2 virtual CPUs, then you've only got a quarter of the possible total CPU available to you, even if it is most busy. It's never going to go beyond that. The configuration for Fargate's very similar. You use task definitions with only a few minor changes for specifying Fargate. An important thing here is that networking is always what they call AWS VPC. This is a custom form of Docker network that uses ENIs, elastic network interfaces, under the hood. This means you can do things like specify security groups at an individual task level or container level, but it does mean it's going to be using one of your IP addresses from your subnet. Now, you don't have a shared server here. You can't access the host that the container's running on anymore. So you can't run a daemon task anymore, so you have to use a sidecar if you want to run an agent like X-ray or bundle it into the original container. Now, one of the big benefits here is if you want to scale up and down with Fargate, it's much more straightforward because you're just scaling those tasks. You don't care about the underlying hardware. One of the problems with scaling with ECS on EC2 is that at some point you run out of space on your EC2 instances. So as well as scaling your services themselves, you also have to scale the underlying auto-scaling groups of EC2 instances, and that can be kind of a pain to get right. And you inevitably end up with some wastage there where you have to have more EC2 instances than you strictly need to account for scaling of the actual tasks themselves. Now, given some of those benefits, why isn't everyone using Fargate? And really the big reason is cost. When this was first launched, it was really expensive. It's still kind of expensive, but they did make a big price cut, up to 50% for some CPU memory combinations fairly recently. And this was when they announced that they were using what they called Firecracker VM technology, which is a very lightweight VM that allows them to, on the same physical hardware, create lightweight VMs to isolate containers between their different customers because it's all multi-tenancy. And this has allowed them to reduce their costs, and they've passed some of that on to us. But it's still expensive compared to well-utilized EC2 instances, especially if you're using reserved instances. If you're interested in the pricing, there's a good comparison I've linked here that really gave the idea that even with these price cuts, Fargate's comparable to an on-demand EC2 instance that's utilized about 70%, which is typically where you are with EC2 instances because you've got to have some headway for running new containers. Now, on the other side of things, EKS is Managed Kubernetes in AWS. Its full name is the Amazon Elastic Container Service for Kubernetes, so we're just going to call it EKS. Now, if you're not aware, Kubernetes has really become the predominant orchestration option for Docker. And this is just as in AWS. It really comes from Google originally, from their internal Borg service. And they have the most sophisticated, up-to-date option for Kubernetes. And it's very core to Google's cloud strategy. And this is where I got the cape from the Cloud Next conference a few weeks ago. Now, Azure has the Azure Kubernetes service, and Amazon has EKS. Azure seems to be somewhat more involved with Kubernetes development than Amazon is, but not as much as Google. I would say the GCP option is definitely the most mature. Both AKS and EKS were launched last year in 2018. And there's somewhat of a sense that AWS felt like they had to launch a managed service for Kubernetes because everyone else had one, and perhaps they rushed putting it out a bit. And it's gone through a lot of rapid evolution since it was originally launched, some of which has required a lot of reconfiguration of clusters. Now, that's not to say you couldn't run Kubernetes in AWS for a long time. A lot of people have been just running Kubernetes on EC2 instances using various tools like kops. And that means that actually Kubernetes itself in its code has support for various AWS resources, like creating load balancers and using EBS volumes as persistent storage. So when we talk about this being a managed option, what does it actually manage? So if we look at a diagram of how Kubernetes is structured, there's a lot of things that are grouped under this master heading. And then running your actual containers, you have, here they call them Kubernetes minions, or they might be called node instances as well. So really the managed portion of this is Amazon running those master instances, and they run 3 master instances in different availability zones. And you don't have any access to that. It's really just a black box to you. Now that's great. That gives you great high availability, but you don't have any choice. You get 3 always, and you pay for that. You don't have the option like you do in GCP of saying, well, I want it just in a single availability zone, or I want the high availability option and different pricing. Here, you're always going to get 3. So if you want to use EKS, there's a bunch of different things you need to do. Now, you need a VPC to run this in. You need a service role. You need your cluster, and then you need those node instances. Amazon provides you CloudFormation templates to set some of this up, and you can create your own custom CloudFormation templates. There's an AMI for EKS that bootstraps and registers with the cluster, kind of similar to the way EC2 and ECS works. But it takes a while for that to stand up. And once you've created that cluster, perhaps you used CloudFormation, then you've still got to configure the kube control command line to have access to that cluster, and then you would use normal Kubernetes tools and templates to register your services. So you've got a split between the technologies you use to provision the cluster and deploy the services, unlike with ECS where you can do everything in CloudFormation. One of the big gotchas here is unlike ECS, you pay for just having that cluster in addition to the EC2 instances that you're going to be running. And while it's not a great deal, it's 20 cents an hour, that's about $140 a month. So for an enterprise, that's nothing. For an individual developer, you might not want to keep one of these running all the time if you're not using it. Now, I mentioned that it can be a bit of a pain to stand up your cluster. It's got a lot easier over time than when they first launched it. Gone are some of the sort of 10-step procedures you previously had to do. But if you want a really easy way of standing up a cluster, then you might want to look at EKS control. This is actually from Weaveworks. It's not something AWS created, but they're using all of the AWS APIs behind the scenes. And here's an example of a very simple command, just EKS control, create cluster, specifying profile and region, and it did everything to stand up a cluster. There's a lot of different options you can give to this. You can use an existing VPC. In this example, it created a new VPC, but you can use an existing VPC. You can install Helm automatically, and lots of different options. So this is a nice way of managing an EKS cluster. They're gradually improving this. So at the moment, it's all command line flags, but in future, it's going to have the ability to run off a configuration file. So if you can do what they call git ops, where you just version your configuration in a template, and you can just apply that and modify the cluster. In terms of integration with other AWS services, here it's a bit more of a hassle than it is with ECS. So as I mentioned, Kubernetes itself supports classic load balancers and network load balancers, but it doesn't, at the moment, support application load balancers. Now, if you want to get that same sort of behavior, so application load balancers can route traffic based upon the host name or the path in the URL or other things, well, you can use Nginx ingress. That's fairly common in different Kubernetes clusters, or there is an ALB ingress controller. That's another open source project that you have to install into your cluster. If you want to get that IAM pod level permission, and pod's very similar to a task in ECS, you're going to need to install something like kube to IAM. If you want your load balancers that are created, if you say a services type load balancer, that's going to create a load balancer. It's got an IP address or a pair of IP addresses and a really long DNS name that you're never going to give to anyone. If you want that to have a friendly name that's in Route 53, well, you're going to need to install external DNS. Making logs accessible, again, that's a bit more of a hassle, and metrics as well. And to install some of these things, you might need to first install Helm so that you can install those into the cluster. Now, one of the nice things about EKS control is that it can automate some of that for you. But a lot of these extra services you need to install are going to be consuming memory and CPU on your node instances before you've even run a service for yourself. And different types of EC2 instances have limits on the number of pods they can run. So you can start to run out of space even before you start running your own service. Now, if you're interested in knowing what EKS looks like, this is pretty much all the information you get about a cluster in EKS. It's not a lot. It's not the sort of fancy visualization that you would get in GCP or even in Azure. They give you a lot more information about your cluster. That's not to say you can't install dashboards within your cluster that give you much more information, and the kube control will give you all the details about the cluster. But they haven't really integrated it into the management console. One of the big promises of Kubernetes is portability across different cloud vendors. But there is significant variance between what you get in a Kubernetes cluster when you start between the different vendors. They have different versions available, different software pre-installed, different services pre-installed. So you've got to account for that when you spin up things. Also, if you want to make use of specific features within a given cloud provider, you're going to need to do things like annotations within your Kubernetes templates. For example, if you're spinning up a load balancer for a service, if you want that load balancer to have logs to go to S3, which is a feature of the load balancers in AWS, you need to add annotations to your template. So if you want to use the same template for multiple cloud providers, you may find that it's got a bunch of different annotations for different cloud providers. Having said that, at the root of it, the actual service, the container you're running, really is isolated from a lot of that. It has its configuration injected in a standard way, and it doesn't really care or know which service it's running in. So if you're not using particular AWS services like Dynamo or S3, then that can be a very portable service between Kubernetes providers. Now I'm going to briefly mention Elastic Beanstalk. This is more out of completeness than anything. Elastic Beanstalk is really an option for easily running lots of different languages, and it's really a layer on top of other AWS services. It's a platform as a service for a variety of languages. And I think one of the real reasons that Beanstalk exists is to make it easy to migrate existing applications, potentially from on-premise onto AWS, without having to learn a lot about AWS behind the scenes. This is going to manage your infrastructure, your EC2 instances, your load balancers. It's going to handle things like deployments and logging. It can also create databases and other related services. Now, for containers, for Docker, they've had a couple of different versions. So actually, the very first option for containers in AWS was Elastic Beanstalk, what they called the single container version, version 1. And this could run a single container per EC2 instance. That's not really the most efficient use of containers. It does allow portability of that container, but you're not packing them in very well, so you're probably using a lot more EC2 instances than you would strictly need. And it also runs Nginx as a proxy. One of the interesting features of this was they allowed you to upload your code, including your Docker file, and it would build the container and deploy it. Now along came ECS, and very shortly afterwards they released version 2 with multiple container support, and behind the scenes it's using ECS. And in this case, it can now only use pre-built images. Now I would say, if you're going to be using ECS behind the scenes anyway, why not learn how ECS works? Because then you get all the functionality that ECS offers you, and you're not constrained by this other layer of abstraction. It may be a good option for other things, like Java applications, web applications that you can easily deploy to Tomcat, but I wouldn't recommend it for Docker. Now, if you're in the previous session, there was quite a bit of coverage of CloudMap as a service discovery option. This is a fairly new service, as was mentioned there, and I'm not going to talk a lot about it because I don't want to duplicate what's already been talked about. This did originally start as ECS service discovery, basically a managed service discovery for ECS that put records into DNS in Route 53 using this namespace concept. This would put either A records, that's just an IP address, which assumes you know the port number, or service records with IP and port numbers. So you could look up a particular port. And this allowed you to query a DNS for available services, and then the client would have to pick one of those, so the client's responsible for load balancing there and making the call to that IP and port number. Now, in order for you to use this, you had to use AWS VPC networking. This could either be Fargate that always uses that, or you could do that on EC2 instances. But EC2 instances can't actually run many things with that option because you could only attach so many ENIs to an EC2 instance. So its applicability is a little limited, or you have to use that more costly Fargate option. They are actually looking at increasing the density of ENIs you can have on EC2 instances that would make this a more attractive option. So when they changed this and made this CloudMap, they started creating an API for it instead of just relying on DNS. You can still use DNS, but not everything really works well with DNS. So what's the DNS for an SQS queue or something else more abstract like that? So it allows you to put things into the API-based system where DNS really doesn't fit because you can't return an IP address for it. And it's obviously got that support for ECS out the box, so anything that you were previously using service discovery would now be in CloudMap instead. And they added support for EKS as well, using external DNS, and support for a bunch of other services. And as discussed in the other session, this is very similar to the service discovery portions of HashiCorp console. Now, how does that look? This is a diagram from AWS. It's really just giving an example of static versus dynamic lookups. So in the first example, the front end calling the back end has been statically configured to talk to version 1, and you now want it to talk to version 2. So it's a configuration change and a deployment in order to get it to talk to the second version. Now, once you've got CloudMap in the picture, you're going to be looking up every time you want to make a call to say, what version should I call? And think of CloudMap as really being an alias. And you can change that alias without the service knowing about it. So it's just calling service 2. It doesn't care about which version. And you just change the mapping in CloudMap, and now it's pointing to version 2, and suddenly the front end's talking to the new version of the back end, dynamically without either being deployed or updated directly. In this rather contrived example that they give, you've got a whole bunch of different services using CloudMap. You've got EKS calling ECS, calling Lambda, calling S3, and there's some EC2 auto-scaling groups in there. And this is really just to illustrate that all those different things can go into CloudMap, and the way they're named on the right is using different namespaces. Now, where I think this really gets interesting is when we start talking about meshes. So meshes are really the next level beyond service discovery, where all the traffic is being managed by something external to your services themselves. With CloudMap, your client service is responsible for knowing where the service discovery server is, looking up, getting that list back of available services, and making a decision about which one to call. With the mesh now handles that responsibility. Now, AppMesh is very new. It only was technically released, generally available in the last few weeks. Still in early stages, although one of the nice things is they have actually published a roadmap for AppMesh, and they've actually started doing that for ECS and EKS. For most things, AWS is still very cagey about what's going to be available when. They won't even tell you in private. So this is nice that we have some idea of how this service is going to evolve. Now, this does make use of an Envoy proxy, and the way that works is every container, if you're running ECS or EKS, has a proxy in front of it, and that proxy handles all inbound traffic and all outbound traffic, so it has complete control over what your service can talk to. And it can transparently change what your service talks to without your service being aware of it. In this case, it's using the Envoy proxy, the open source Envoy proxy, the same proxy that's used by other meshes like Istio. I think the real reason AWS didn't extend something like Istio is they want to inject this into all of their different services. So they want AppMesh to work with things like Lambda functions, ECS and EKS, all in a very similar way, and having control of that mesh gives them that ability. Now, once you've got that mesh, it gives you the ability to do things like traffic shaping. So this might be routing where you do canary and A/B testing. Now, you can do some of that with CloudMap, but the client's got to be aware of it. It's got to be supplying selectors to say, give me version 2, or give me the latest version, or the canary version. In this example, the service has no idea that it suddenly had 5% of its traffic routed to a new version of the service. It's all handled by the mesh. And the mesh can try that out, test whether it's healthy, and then go back to sending everything to the old version. It gives you that built-in load balancer and integration with service discovery like CloudMap. And handling failures, the ability to do retry policies and circuit breakers. So if you've done that yourself, you've had to write that into your application previously when you were calling another service. Now the mesh is going to do all of that for you, and you can standardize this as a policy across your entire mesh, and not just for each individual service have to configure that. So that can be really powerful. Now, they've also added integration with things like CloudWatch and in particular X-Ray. So you can see in X-Ray all those calls between your different services, and if you are splitting traffic between two different versions of the service, you can see that in your X-Ray console. Now, a very simple diagram of how this might look. In this case, we've got service A, and it's calling some version of service B. In this case, there's 2 copies of the original version of B and a B prime that's running 2 copies as well. But A doesn't need to know which of those it's calling, because this virtual router that sits in the proxy is handling all that traffic management. Now, as I mentioned, yeah, you probably can't read that. This is the roadmap. It just gives you a sense of the different things that are completed, in progress, coming soon, or that they're researching. So it's really nice to have an idea of the things that they're adding, and it also gives you the ability to petition for things they haven't considered yet. In the coming soon is that circuit breaker and retry policies, so those aren't available today, but they will be soon. And things they're researching using ECS without using AWS VPC, so you wouldn't have to use those ENIs. Mutual TLS between services, which is a fairly standard thing for app meshes like Istio, and Lambda function integration. So this is going to evolve over time. I think it's something that people who are running microservices in AWS should start evaluating and see whether it's a good fit for them, but I wouldn't necessarily be using it in production yet. If you want some more details on this, they have on GitHub an example project, and this contains basically a walkthrough of the same application being set up with app mesh in both ECS and EKS, and documents all the steps you need to get started. And it does include things like sidecar injection for EKS, so rather than you having to set up your pods manually with the Envoy proxy, it'll automatically inject that proxy for you. So that really was all the orchestration side of things. So I'm going to quickly talk about a couple of options that are outside orchestration that also make use of containers behind the scenes. The first one of these is AWS Batch. So this is often used for batch processing of large amounts of data where you want something done, but you don't necessarily care about exactly when it gets finished. Now, here we have a batch service that automatically provisions all the computing resources for you. You don't have to stand up EC2 instances manually. And it has the concept of a job, which is a unit of work. It might be something like a shell script, Linux executable, or you might actually supply the container you want to run directly. And a job definition where you specify an IAM role, some CPU and memory requirements, and this looks very similar to an ECS task definition. And then you've got a job queue, and you can have multiple queues, and you can prioritize your work based upon which queues these go into. Now behind the scenes, surprise, surprise, the jobs are run as Docker containers on ECS. See, one of the nice features of this though, and you can do this with regular ECS as well, is it runs on spot instances typically. Spot instances are where you're bidding for unused EC2 capacity and you can save a lot of money potentially, but they may be terminated with very short notice. But that's perfect for batch work if you've built your batch jobs properly so that they can support being terminated with short notice and retry from where they started and where you've split it up into individual pieces of work. An entirely different use of containers is CodeBuild. Now it's become very common in newer CI/CD solutions to use containers. And one of the real benefits of using a container-based CI/CD pipeline is you can put all your dependencies, all your tools within a container and repeatedly use that, always starting from the same point, having consistency. Anything that got changed during your build gets thrown away, so you don't have to worry about your server being polluted with artifacts. And you don't have to worry about, well, someone's installed this tool on our Jenkins server or our Bamboo server, but we can't remember quite what they did to configure it. But it works, but we want to go to a new server, but we can't remember how it was set up. Well, now, your actual host instances, your EC2 instances, if you're running some of the other services, or in CodeBuild you don't even have access to that, they're very basic. They just need to run Docker, and it's your container that has all the special logic they need for building Java, building .NET. So everything's Docker-based, and you can do builds and tests and packaging within CodeBuild. All steps run in Docker containers, and they supply a whole bunch of CodeBuild containers that are pre-installed with common development tools, like Maven and Gradle for Java, or like the .NET tools for .NET Core. There is also support for building for Windows, so .NET Framework. And this makes use of Windows containers running on Windows servers behind the scenes. That's kind of nice because some of these container-based options don't support Windows. It's commonly integrated with Code Pipeline. This isn't really a full CI/CD solution by itself. It's just part of the solution. It's that CI portion. It's typically you use Code Pipeline to kick off a build or to manage the deployment after the packaging done in CodeBuild. And it scales automatically. Rather than you having to worry about provisioning different agents under the hood, it'll just automatically scale based upon how many jobs you've got to run. And you pay for the build minutes. So in this case, the first 100 build minutes are free per month, and then you pay on top of that. So if you've just got some small usage, this is quite a nice option to start with. Okay, and that was really all the different options. I don't want to drag out too long, but if anyone's got questions, I can either take them now or anything via Slack. And apparently everyone wants their lunch.